Good evening, everybody, and a very warm welcome on a chilly night to Imperial College London. I'm delighted to be here tonight. My name is Hugh Brady. For those of you who I haven't met, had the pleasure of being president of Imperial for approximately 16 months, and it's just wonderful to be here, both to celebrate both the renewal of our partnership with TUM, but also to mark the occasion with a discussion of one of our partnership research priority areas, achieving a sustainable zero pollution future. My first visit, Thomas, actually, as president of Imperial, I think was to your campus, and I must say, at that time, memorable because these seemed like twin brothers or sisters, twins, in terms of the DNA of the institution, the quality of the research and education, and the real passion for innovation. And it was at that event almost a year ago that we launched our Zero Pollution Initiative. So it's wonderful to have TUM's president, Thomas Hofmann, and his TUM colleagues join us to co-host this event this evening. Professor Hofmann, in both his position as president of TUM, but also as, and very importantly, as president of the Eurotech Alliance, has been a steadfast supporter of international collaboration, and very importantly for us, a advocate for the UK's association with Horizon Europe. So for everything that you've have been doing over the past few years to make that happen. I know I speak for everyone in the Imperial science community when I say how thrilled we were that the UK's association has now been formally agreed. As a university president, you get all types of emails, but I've never, the volume of enthusiastic and quite joyous emails when the association was announced, I think certainly for me was a barometer of the importance of that European relationship. So a big thank you to our TUM colleagues for all that they've done. And then of course that's been built upon by new agreement between UKRI and Germany's DFG, and a new declaration between the UK and the state of Bavaria. So these are much welcome, much needed mechanisms to support world-class science and innovation in the UK and Germany, and the collaboration between the two countries. For those of you who may not know Imperial well, we're unique in the UK in terms of a focus on STEM and business. And what I really noticed moving to Imperial, and I've always worked in so-called comprehensive universities, was that innovation, impact, translation, and enterprise very much part of the DNA of our institution. You're joining us, of course, here on our relatively new White City campus, which is the anchor of a wider White City innovation district. And certainly, I'd hope you'd agree that it is a shining example of how a world-class research-intensive university can create a new precinct in a relatively short period of time, which is transformational in terms of its own educational research and innovation activities, but which is also a catalyst for urban regeneration and economic growth. I claim no credit for this. We are now planning the next phase. That'll be on my shoulders. But I think those that took those decisions over the past 10 to 15 years deserve great credit. So on this campus, we have industry, government, and startups, both on the campus, but increasingly in the surrounding area, in the surrounding district. And then literally 5 minutes away, we have our Hammersmith Hospital site with a full range of biomedical, clinical, and translational research activities. So it's an innovation ecosystem that is growing and that we're really thrilled to be developing. As I think all of you know in this room, one of the reasons that you're here is the very best collaboration in research and innovation. That is what's required if we're to address the grand challenges of our time. So both the challenges that affect humanity and our planet, but equally the solutions do not respect borders and require perhaps more intensive collaboration than ever. Collaboration is the very fabric of what we do as academics, be it within our institution, across our institutions, and across borders. So signing an institutional partnership agreement with TUM was really exciting when it happened in 2018 for Imperial, and has led to so many successes to date. Numerous cohorts now of collaborative PhDs working between Munich and Imperial, over 70 research seed fund projects, student and PhD experiential learning programs, including research placements, innovative education formats, and seed funds, a program to develop UK-EU networks for early career researchers, and engagement on the development of our respective ecosystems, and including with TUM becoming a founder partner of our Global Challenge Lab. Now, tonight marks the second annual event of our Imperial TUM Zero Pollution Network, and we're focusing on sustainable mobility. We have a fantastic keynote speaker, Dr. Mark Bentel from Airbus, and many of his colleagues I know are also here, and a panel discussion really to provoke discussion and ideas as to how we can reach and engage more people from our London and Munich ecosystems in this vital work. I know my engineering colleagues always remind me that it's taken a long time to develop truly innovative technologies that are working to develop sustainable transport. And the challenge for us now is how can we accelerate this given the carbon imperative, and how can we work together to accelerate the innovation timeline. And I know that, again, the reason that you're all enthusiastic about this event and this partnership is because we're up for that challenge. Imperial and TUM see many opportunities to do more together in zero pollution, as well as in other areas to address global challenges. And I'm particularly thrilled. I'm a nephrologist by background, no longer licensed nor insured, but I am a clinician scientist. So I was delighted that our Faculty of Medicine and TUM's School of Medicine and Health just a few weeks ago met in Munich and identified a number of exciting issues that we think that we can very fruitfully collaborate with at scale. And I think Thomas will say a little bit more about this in a few minutes. So it's my great pleasure to invite President Thomas Hofmann to join me and tell you about TUM and the ambitions we have collectively for the next stage of our partnership. So thank you for joining us this evening, Thomas.
Dear you, first of all, thank you so much. First of all, for giving your first visit last year to TUM, we really appreciate that, because I know I'm now president since 4 years, how busy the time is, in particular in the first year, and that you selected our university as your first visit, we really appreciate that. My name is Thomas Hofmann. I'm the president of TUM now since 4 years, and first of all, I would like to thank you. Because you all and the faculty members, the colleagues, the PhDs, postdocs, you are the ones to drive this partnership, actually. We as presidents can only give some kind of future ideas and visions and can try to make your work a bit easier, right? But I think this partnership is really carried on your shoulders. In particular, I would say, I have to congratulate you and Imperial for this wonderful White City campus, because I was here last time, 2019. At that time, I think there were 2 or 3 buildings. And now, if you're here again, it looks quite a bit different. And I can only imagine how it would look like in 4 years to come. Although I promise I will come earlier. If you look now, after 5 years of this collaboration, if you look back, you're absolutely right what you said. We have great successes in numbers, also almost 100% more joint publications than we had in the past. But I think the true success is probably the trust which we built between both institutions, between Imperial colleagues and TUM. And everybody knows that good science is built on trust. Without trusting each other, when we share information, when we share knowledge, when we share ideas, I think the best science would not come out. And if this, next to the trustedness, to the trust of our partnership, we create a vivid interaction. so that people really want to collaborate and want to be active, want to look for the interactivity where we can put the best forces together, I think then we really do a good job, and you did an excellent job over the last 5 years. If you look, if you compare 2018, that was the founding year of this partnership, with 2023, it feels like a bit that we live in a different world. We have so profound changes in this world and challenges which we have not foreseen at that point of time, 2018. Even more, it was important to enter into this partnership, because if you look today, the climate change is still unbroken, and all the consequences of this challenge. If you look at the geopolitical disruptions which we see worldwide, also starts to hinder free science, partially, more and more, something which the world has not seen since 60, 70 years, right? I think science is even more challenged, and that's why partnerships are so important, going beyond the countries and continents. And that's why we are really proud. And if we could do a little bit to overcome, so to say, some of the Brexit hurdles, which you mentioned, at least that you can participate again in EU programs, I think then we already did a very good job. And I would like to thank you really for this partnership. If you, you just mentioned the economic impact of universities, and I cannot agree more. I think universities need to redefine also their mandate, why we are here. And we are paid as state-funded university. We are funded by the state, by taxpayers' money. So also we need to do something that we give something back to society. And that's why it's so important that we first of all tackle the important challenges. Secondly, that we put everything on the ground and put our resources to action, that we really translate our findings in the laboratories into societal applications to bring this impact to the people and the economy. Because otherwise, I think even our universities won't have a successful future. And we exchanged on that half an hour ago. I think if you compare Europe today to United States or to China, we are really good with good ideas, with creativity, and putting ideas from 0 to 1, but we are still too reluctant bringing technologies from 1 to 100. And this is where China and United States is great, much better than we are. And that's why the scaling ideas and scaling technologies and application should be on our future focus in the next years to come, for the next 5 years to come. And that's also why it makes me proud that I can announce the Zero Pollution Advance Fund, a fund which we will put together, Imperial and TUM, to invest in great ideas and to pushing those ideas to the next level. This will be an element of the document which we will sign today. If you then see what else is needed next to the partnership of strong scientific institutions, I think it's the rootedness of both institutions in their local ecosystems. London and Munich, I think, are just great places to live. It's expensive, okay, on both sides. But on the other hand, they are highly attractive places for top talents, to bring top talents from all over the world to London and Munich. And then it's also an attractant for global companies, for tech companies. And if you compare, if you look at London and Munich, I think they are more or less uncomparable to other cities in Europe. I think what we have here on both sides is top science combined with top industry partners and technology. That's a great asset. So we also need to bring those ecosystems closer together. And then we'll probably also speed up acceleration of technologies into real applications. So I think through this partnership, we may expand also building bridges to our economic systems and to the industrial partners. And therefore, I really would like to thank also the industrial partners from Airbus and others that you are here today, because it's not only about universities. Universities are the core because we create the new people, the new generation of talents. But we need to build bridges in order to accelerate innovations to come to reality. So I would like to thank you again. I would like to thank you for all what you have done so far, and I hope that you are even more energetic for the next 5 years to come. I would like to thank you for believing, for trusting, and for engaging in this partnership. Thank you, and hopefully that we see us again next year with more successes. Thank you.
We're going to take 1 minute to sign our renewal agreement. A few photo opportunities, removal of plant, I hope. Good. I'm going to invite Professor Mary Ryan, our Vice Provost for Research and Enterprise, who's going to introduce our guest speaker on the panel discussion. Mary.
Great. Well, thank you, and thank you both for those kind words. The work we've been doing in the last year on the Zero Pollution Network, I think, has been really inspirational, and the teams that we brought together are really driving a whole lot of technology advances and beyond technology. In the Zero Pollution framework, that we could have picked 30 or 40 or 50 topics to talk about. It is an all-encompassing system when you start to think about the challenge that we have to get to decarbonisation, to biodiversity protection, to chemical pollution. We decided we didn't have time to do all of that, so we would take a slice of the Zero Pollution Challenge. And so tonight we're going to have a talk by one of our great industrial colleagues and partners, and then a short panel discussion to think really about how we move towards sustainable aviation. Right, so that's the small slice. You'll have to come back for the other slices of the puzzle. So we're going to start with, a small provocation from our guest speaker, and then a panel discussion from academics from Imperial and Munich shortly afterwards. There will be a small chance for some questions from the audience, so I'm not going to pick on anyone, but get thinking. But let me introduce our guest speaker, Dr. Mark Bentel, who's Head of Research and Technology at Airbus. He's been at Airbus for over 27 years, I'm told, currently overseeing the research and technology profile, and responsible really for the strategic goals in research and development. And in particular, I think there's one piece that I'm interested to hear about, the challenge of Airbus's stated ambition to get to a zero-emission aircraft in service by 2035. Mark, thank you.
Thank you very much for the introduction, and thank you to Imperial College London. Thank you to TUM as well for allowing Airbus to take part, and I'm glad it's on aviation and none of the other subjects. Otherwise, it's not really going to work for me. It's a very welcome reinforcement of technological partnership, certainly between Germany and the UK as well. So this is really important. I've been asked to pass on the apologies from our CTO, Sabine Klauke. Unfortunately, she couldn't make it today, but I'm really pleased that Greg Ombach has joined us as well, who heads our disruptive research and technology, and Steve Rains is also here as well from Airbus, who does all of the government relations and partnership relations in the UK. So very pleased to have these guys with me today. So yes, we do live in a globally connected world where business and personal relationships are developed and underpinned to a large extent by air transportation. And aviation gives us that ability to make our distances a lot smaller and our world a lot larger. But we can't ignore the imperative of climate science and the responsibility and opportunity that we have to transform the technology that makes all of that possible. So it's really good to have the opportunity today to walk you through the challenges that this presents to commercial aviation, and how we, Airbus, as a global leader in aerospace, is facing them, and how we're going to handle them head-on with the policymakers, with academia, industry partners across that full value chain. So, if I get this right, first of all, to understand Airbus's key priorities in decarbonisation, we really need to understand the evolution of the aviation market and how we see this unfolding. So let's have a look at commercial aviation's trajectory over the next couple of decades. Now, all of this information you can get from our global market forecast. It's a lot richer and deeper than this. I'm just going to pick a few points out for you, but it is available off the Airbus website. You'll also find one from Boeing. They publish one as well. So you can go and have a look and get into detail. But this is focused on commercial aviation jets. So you will not find in here business jets. You will not find in here military aircraft and anything like that. So the global market forecast is actually based on population evolution, population distribution, and prosperity. Those are the three, what I regard as the main drivers for underpinning the evolution. And if we consider here the approximate lifespan of an aircraft somewhere between 20 and 25 years, then there will be about 17,000 aircraft replacements of the current fleet, what's flying today, and about 23,000 new aircraft coming into service for new routes or to increase capacity. And that will be for growth. Now, this covers both passenger and freighter traffic, but the passenger traffic is 90 to 95%. So we are 99% of the demand of that fleet. We break it down into small, medium, and large. For reference, some of you in the industry might have heard of single aisle, wide body. These are still well-used terms, but we tried to structure it a little bit differently some years ago into small, medium, and large. And in that breakdown, you'll see that 75% of the demand is in the small category, 76%. That's like our A220, our A320neo. But if you actually look at that from a perspective of fuel burn, and it's not on the chart, 50% of the fuel burn comes from the small range, and 50% comes from the long haul and large range. So, or 45%. The rest is in the areas of regional jets. So, what does that fuel burn mean in CO2? So we know the size of the fleet. We know the roughly the fuel demand distribution. What does it mean in CO2? Well, we can only look at our Scope 3 numbers that Airbus publishes on that, which when we took our Scope 3, that's the use of products sold. And for the use of products sold, then Airbus delivered 863 aircraft in 2019. And based on an average in-service life of 22 years, that is about 740 megatons of CO2 for the life of those aircraft, of which 130 is in the manufacture of the fuel. So to give you some reference, the output of Germany for 1 year is 655 megatons of CO2. So the Scope 3 of Airbus, which is half the market with Boeing, is slightly larger than the national output of Germany. So it's quite a significant thing to address. You can also compare it to an oil and gas major. So ExxonMobil was 530 megatons in their Scope 3. So now we have that sort of outlook. What does that mean for the Airbus strategy? Well, in 2019, we unveiled a new company purpose, which was and is to pioneer sustainable aerospace for a safe and united world. That's more than a response to the climate crisis we face. It really is defining who we are, where we're going, and it's a real touchstone for whatever we do. And I'm sure Greg and Steve will know it very, very well. But what does it mean? It means we can't be complacent. It means we deliver products and services that allow us to play a role in addressing climate change. Our aircraft are extremely popular all over the world, but we will never stop trying to make them better. We will always try and improve on that. So we have three. So first of all, we've got to worry about the fleet replacement. You saw on the previous screen, the large part of that is fleet replacement and developing the new. we've got to prepare for the critical technologies that are going to be on the future generations. Today, if we take a look at the overall fleet replacement and new technology, we deliver about 75 aircraft a month. That's our current target. So we need a lot of work on replacement, we need a lot of work on preparing the critical technologies. And, as was already mentioned a little bit in the start, where are we going with new fuels, and specifically with hydrogen, and what does that mean to us? So, let's try and break that down a little bit into some pillars. The challenge of decarbonization is not a surprise. For a number of years now, we've been pressing with the research and development company-wide into a new generation of low-carbon technology, material solutions that contribute to reducing the industry's environmental impact. This is part of a much longer journey that we've been on. So to improve fuel efficiency, over the last years, we've had an 80% reduction in carbon emissions over the last 60 years. So we didn't start this journey today, and we've seen a huge evolution of emissions over that time. And that has come from everything from evolution of thermal performance in the engines, weight reductions, and improvement in aerodynamics. But in 2021, the aviation community did come together in an important target ambition to reach net zero by 2050, and that's in this chart, which is a pretty well-known chart in the aviation industry. And the goal was also endorsed by the ICAO in 2022, which is a major milestone to really get industry synchronized. And I think whenever you hear the aviation industry speak, we are all very much in agreement on what the targets are and generally how to get there. So how do we get there look like? So if I look along the bottom and go from your left to right. So first of all, we've got the latest generation of aircraft. As I mentioned, these are already available. We're building them today at trying to get to around about rate 75. That will address about 75% of the global fleet. So about 75% of the global fleet today are on older platforms, less efficient platforms. So there's a huge opportunity today of replacing that existing older generation with all of our products from the A220 to the X350 XWB. And these aircraft are already providing a 25% reduction in CO2 emissions on average. And if we look at things like it's not in service yet, but the 321 XLR, which we happen to have in service next year, that's a 30% reduction in fuel burn per seat compared to its predecessor. So the demand is clear when we consider the Airbus's order backlog for aircraft. What's currently on order in our books is about 8,000 units. So that's about 10 years worth of production already. So we know of those numbers you saw earlier, we know what 8,000 of them already look like because they've already been ordered. And it's not just commercial aircraft. We have always had significant reduction in CO2 on our commercial helicopters as well by about 30%. So there's the latest generation that can already be brought into service. But then there's also stuff we can do today in terms of operations and infrastructure. This is including airports, air traffic management, and it's estimated to be able to reduce by about 5 to 10%. Now, I really am focusing on CO2. And we'll talk about non-CO2 effects shortly. But here we think things like continuous climb and descent optimizations, flight trajectory optimization, four-dimensional trajectory data, single engine taxi, or some form of hybrid taxi bot to maneuver you around the airport without your engines running. A more extreme example was one that we did recently with a program called Fellow Fly, where we actually tried to mimic what the geese do and fly in a formation so that the aircraft behind can get a lift off the wake of the preceding aircraft. And we did that across the Atlantic, and we proved that we could get about a 6-ton CO2 saving just by doing that with 2 aircraft. So imagine what you can do just with flight operations across the fleet. Next one is sustainable aviation fuels, by far the biggest part of the graph in the green there. So the entire sustainable aviation fuel ecosystem we have to consider from the energy supplier to the airline operator. And that also is underpinned by how we work with the regulators and governments with the support of us, the OEMs, the engine manufacturers, into make sure we've got tangible solutions. So as an interim target, before 2050, there is a general target that SAF uptake by as much as 10% by 2030. Remembering that our aircraft today can take up to 50% sustainable aviation fuel without any modification. Same for Boeing as well. So the tanks of aircraft today are less than 1% filled with sustainable aviation fuel. So we've already got quite a way to go, and we have a target to certify our aircraft to 100% sustainable aviation fuels by 2030. Then we have disruptive technologies. I will go on to that in the next slide. And we have some market-based measures, including regulatory, such as the EU Emission Trading Scheme, CORSIA program for offsetting and voluntary measures, such as through direct air carbon capture. So I mentioned that we don't just look at CO2, and we need to look at non-CO2 effects. And what do we mean by non-CO2? So some people instantly think of things like noise, it's non-CO2, but really, we're really focused here on other emission products, which traditionally are considered to be water vapor and contrails and NOx. Now, this is quite a complicated area, and the science is still out on that one in some extent. We do see, and this will be maybe a discussion point later, in how we can align the science and the priorities, because what comes out of the science really drives our priorities. And we are seeing quite some differences in this area, and so it's a really important one we need to get a grip. And we are working with programs like Seconia through the EU to try and help get some solution. But again, it's a full value chain option, and will heavily potentially impact operations as well. So, if we look at some of the technologies to reach the industry decarbonisation targets, basically we need ultra-efficient aircraft to join the market somewhere between 2035 to 2040. And these have to be more fuel efficient, they have to be 100% sustainable aviation fuel native, and so efficiency is somewhere in the region of 20 to 30%. So not just because you don't want to produce the CO2, but even when you're flying sustainable aviation fuels, they're a lot more expensive. So therefore, you also need to get the fuel burn reduction to cut the cost. So what are some of the solutions to do this? Well, I'm going to focus on two, the wings and the engines. So if you look at it from a sustainability point of view, I always say the best fuel is the fuel you don't need. So how do you get rid of the fuel? Half of that fuel burn reduction has to come from the wings, has to come from the aerodynamics of the aircraft itself, and the majority of that, whenever we do the sums, is through the wings. And what does that mean? The next generation will have wings. They've got to be lighter, they've got to be stronger, we've got to have a larger wingspan, we've got to have a higher aspect ratio. That also brings new challenges. We have programs on folding wingtips because we still have to fit in the same gates around the airport. So we need to bring those technologies. Earlier this summer, we officially opened the Wing Technology Development Centre in Filton, in Bristol. And much of the research on this will take place, not just in terms of design, but also in terms of preparing the industrial system. Remember, if we've got to do 70 aircraft a month, we need 2 wings for every one. So therefore, we've doubled the rate on the wing side. Then the wing is also a very strong collaboration area between UK and Germany, where UK leads on the overall wing design and structure, and Germany leads on the components and such as the movables and the inners as well. So it's a very strong UK-Germany collaboration on the wing area. The other 50% has got to come from the engines, okay? And the engines, Airbus is not a gas turbine manufacturer. Okay, there are a number of engine OEMs out there. They are all having different approaches and different designs to try and address the engine efficiency and improve that. They all result typically in bigger fans and bigger bypass ratios. Thermodynamics plays a very important role, but you're constantly trading NOx with CO2 when you go down that road. So again, really comes back to understanding that NOx impact is really, really important to make that decision. We have engines which are coming with ultra-high burst pass ratios. We have engine concepts coming for open fans, so engines without a nacelle, and other concepts for future improvement of the performance. Our focus is how you integrate that onto the airframe and what the implications of doing that are. There's no point in putting on an ultra-efficient engine if you've then suddenly lost all those efficiencies when you've gone and put them on the airframe and you've lost it aerodynamically, or you've lost it through having to put extra protections on or whatever, engine separation, blade release. So later this year, later this decade, we will be flying the open fan engine from CFM, the RISE engine on this A380 as a demonstration platform. Now, we don't stop at sustainability. I'm just going to use those two today, but there are a number of other topics. Sustainability is also about circularity of materials, energy use in our production. We also have to worry about then manufacturing in terms of robotics, improved automation. We have to worry about connectivity of the aircraft. We have to worry about the autonomy. We have to worry about all of these other things. So though none of that goes away just because we've focused a little bit here today on sustainability. So, Zero E, you mentioned Zero E. I would just say a few words and then we'll probably take some questions. So we've been quite vocal in the past few years on one of our more disruptive programs, which is Zero E. So the whole purpose here is to deliver a hydrogen-powered aircraft with a target in-service date of 2035. And the program launch, if we were to go for it, would be somewhere towards between 27 and probably the end of the decade. We'll have to make that decision. First of all, we need to secure the technologies in order to do that, because there's a load of technologies we need. That's everything. So we've been exploring both hydrogen fuel cell powered aircraft and direct hydrogen burn. And those are both perfectly valid routes that we will explore to see if we can find the best, and they will probably end up in slightly different market segments, and we'll have to see how that all times out in the end. So the way we currently are working on that, our focus is really on the hydrogen fuel system and the propulsion system today. So you won't see much from us apart from concept designs and things like that. Once we've really got to grips with the fuel system and the propulsion system, then we will then go into the details of what the actual aircraft starts to look like, because those things will heavily drive what that aircraft is, what its mission performance can be, and where it's going to be in the market. So a lot of that research focus today, and we're making very good progress. I'm very, very proud of the e-aircraft system house we have in Ottobrunn in Munich. It's something that I've followed for many, many years and been involved in. And this year we ran a 1.2 megawatt fuel cell power stack all the way through to a load on the end. So this is the first time we've done that. Other people have taken things to flight. We will take things into flight, but we need to try and do it in a way where we bring the certification authorities along the road in the atmosphere, in the upper atmosphere. Yes, we can learn a lot from space. We are fortunate, Airbus has a space organization, so we can learn a lot, but we will have to build an aircraft that withstands about 20,000 cycles. The rocket's not so. Elon Musk is doing well. I give him credit. You know, he's got reusability, but not quite to that level. Obviously, we have to refuel the aircraft. We have to sit on the runway. We have to have a much lower boil off. So there's a lot of different challenges. But we are trying to bring a lot of those technologies and competencies through. So, areas for collaboration. It's becoming clear how essential cross-collaboration in building these technology bricks is. We've been specifically quite vocal on these things because collaboration is so fundamentally important to make this happen. We cannot do it alone. That is absolutely clear. Industry collaboration on technology. I mean, earlier in these past few years, we did an example of the teaming with Elring Klinger on doing fuel cells. So they were coming from the automotive industry. We set up a company called Aerostack to look at how we can get the fuel cell density for aviation. Another example is on a program we've got called Blue Condor, where we actually put hydrogen gas turbines, or we modified a very small gas turbine, and we put it on a powered glider that can fly at altitude so that we can do tests, and we're very proud we flew that. It's in Greg's team. We flew that just last week or the week before, so extremely proud of that. And we are doing a lot of other tests with Rolls-Royce, DLR, Neste, Manchester, Canada, on testing different aviation fuels, how they impact the aircraft, what emissions do they put into the environment. Academic partnerships are also fundamental. I mentioned non-CO2. I'll mention it again because it is a really important one. Non-CO2 emission implications associated with the impact of contrails, associated with the impact of nitrogen oxides, how that can be offset with different air traffic management operations, what that really is. We see a lot of charts, we see a lot of ambition coming on that. So we really need to understand how that can be done, because if, one of the reasons we want to test hydrogen is because it will produce more water. And so we don't want to produce more contrails, and someone say, well, actually, that's worse than where you started. That would be complete the wrong thing. So we are testing and we're trying to fly, but when you speak to a lot of the academics, you say, how well are your hydrogen models? They say, hydrogen models don't work. Okay, so maybe we need to work more on that. So this is really important, and the UK and Germany are really, really significant countries in this. Certainly with the likes of DLR, MMU, they are right at the front end. They are in the IPCC. They're writing the reports, so they are right at that part. But also cryogenic materials, how composites can survive cryogenic temperatures, systems, pumps, valves, hoses, pipes, connectors, high-performance batteries, electrical systems, all of this we need to take to the levels that aviation requires. And that is going to be fundamentally important, collaboration with academia. I should give a special mention to TUM, with who we're working with the Aerospace Connect collaboration. That collaboration has brought many benefits from both parties, including strong links between the Airbus faculty teaching and the faculty teaching research staff, as well as our SME ecosystem at the Ludwig Bolko campus in Ottobrunn. And we work with TUM also on across projects outside of commercial aviation, and certainly on eVTOLs and urban air mobility as well. I've not mentioned any of that today, but there's a lot of activities going on there. And with Imperial College, we are part of a collaborative research program on laminar flow control, and that's work with the Department of Mathematics, and that is to really look at drag reduction on the aircraft, helping ensure that we can achieve those wing targets that we mentioned earlier. Lastly, securing investment. Securing investment in aerospace is really, really important because it's, as you see, it's a long-term game. I know it's one of the questions, but it's a long-term game, and we're really pleased that the UK announced the long terms with the extension of the ATI program out to 2030. So that's excellent, excellent news. And having horizons is super important for us. There's not one major assembly on that aircraft which is not multinational. And to do the research, we need to do it in a multinational way. We were quite vocal with the authorities on the importance of coming back into horizons from the UK. And we're absolutely delighted, and I'm pleased everyone else is recognized. I remember the day there was a big cheer coming. I got a lot of emails from the academic community. So in conclusion, at Airbus, our role is to pioneer sustainable aerospace for a safe and united world, striking a balance between the continuous incremental innovation and disruptive challenges. The demand for air travel is increasing. The impact doesn't have to, and that's the key point. We've got a credible path. There's a lot of new technology behind it. Our research and technology partnerships are absolutely fundamentally important. We're absolutely headed in the right direction. So now it's about time of keeping up that pace. That sky is not the limit, it's just our launch pad. Thank you. I'm sorry I overran.
I'm just going to jump straight into the discussion, and there'll be time for some questions afterwards. So if you'd like to take a seat, and if the rest of my panel could join me, please. I do. Right, I'm just going to grab some water because I'm coughing, otherwise I'll be coughing at you. So, I would like to introduce Professor Rafael Palacios, who is a professor of computational aeroelasticity and who is the director of our Bramall Vesuvidevan Institute for Sustainable Aviation. Professor Laura Mainini, is the chair of aerospace computational design, recently joined Imperial College, and Professor Rolf Merkel, who's a professor in travel behavior at TU Munich. So thank you for joining us. Rafa, I'm going to come to you first, just briefly. Can you just give us a summary of what the Institute for Sustainable Aviation is doing, or is hoping to do?
Exactly. We started a year ago, for you that haven't heard about it. We are that slice that you were referring to before, how you bring net zero into aviation. Is this ongoing? Okay, thank you. So, of course, we had a Department of Aeronautics that stayed for about 104 years now. Now we have a challenge, which is at the level beyond what we were doing as a discipline, and that's what our observation we have. So we've been effectively three things. So the first one is we're bringing net zero into our curriculum. So we are training engineers which are ready to tackle this challenge, and that's one of the key areas of the university. The second, we're building teams which are across university. So these challenges are not just us, it's us learning about fuels and hydrogen and contrails and you name it, and those happens in various places of the university. And the third is the critical element, which we are also providing that additional evidence to make those policy decisions, because a lot of this is policy driven. So when I have make sure we have a voice there which is impartial and informed.
Okay, SAF. All right, we heard a lot about sustainable aviation fuels in your talk. We hear a lot about it taking out a lot of the carbon. So I guess, first of all, is solving the SAF problem really going to be such a silver bullet? And I'm interested in thinking about what is the source of the SAF? Where is it coming? How does that compete with other uses for fuels, technologies, land use? The kind of broader picture on the fuels.
Exactly.
Where are we getting it from at scale in the next few years?
I wish we had an answer, right? That's precisely, that's one of the challenges.
Okay, let me ask you a question. What are the challenges in delivering sustainable aviation fuels at scale?
The challenge is what you just mentioned. So we need to create the industry as we're creating the solution. We have the airplanes which are already flying, but we don't really have the industry which are going to be able to provide that fuel at the scale that we need and the time frames that we need. And this is what a huge pressure of this comes from the policy side. So our colleagues in one of the institutes, System Molecular Science and Engineering, did a fantastic exercise early this year. They collected all the evidence about this and put a very nice white paper out there you might have seen already. So the main conclusion is that the only long-term solution that right now we know exists is what we call power to liquid. That means producing fuel out of electricity. And that needs a lot of electricity. That's a challenge.
Maybe Mark wants to speak to this. What scale are we talking about? Because I think often when we think about the decarbonisation process across all industries, we think we've got a technology or a solution, and it won't scale. So where is the scale challenge in this space?
I don't have the numbers to hand, I'm afraid. But I think what encourages, I've seen it as a phase. So what encourages me at the moment is I see lots of different feedstocks and different routes to SAF, okay? So I don't think there will be any one approach to SAF, certainly in the long term. PTL is clearly where we need to get to, but that, again, due to the energy demands, that's going to be some way in the future. So in the shorter term, encouraging all of those different feedstocks, because it will only be a blend of all of them that I think can get close to where we need to get to. That then raises the important point that we need standardization. Okay, it's quite interesting because we've been reliant on kerosene, and actually some of the parameters of kerosene were never standardized because it's what kerosene does. And so we need to now standardize what SAF means, and we also have the difference between drop-in and non-drop-in SAF. Yeah, so when we talk about a 50% blend on the aircraft, that is to accommodate that. So you can put non-drop-in SAF into an existing aircraft, so you don't have to put additives in and aromatics because you're relying on the existing fuel. Yeah? So you've got to take that into consideration as well, and the additives are about 20% of the volume. So it's going to be a multiple dimension problem of multiple feedstocks, long-term evolution in energy, standardization, and then ultimately bringing that new generation of aircraft through that can take that blend.
Okay, and Rafa hinted at this about we're effectively, when you think about the aviation piece, or I guess across the piece when we think about new fuels in general, creating entirely new industries and new supply chain.
Yep.
And so what's Airbus's approach to that kind of broader system piece that sits kind of outside of your core business? But
So we are actively monitoring it. So we are trying to figure out the best way to monitor the SAF production and, more importantly, the SAF usage. As we said, less than 1% of the tanks today have SAF in. And we're following the airlines. They're all making, or a lot of the airlines, I think the ones that contribute about 50% of the fuel usage, when I last looked at the numbers, they are all targeting 10% utilization. So then it's for us to, we're tracking that, we're making sure it's happening. We're also investing in that. We're supporting some of the funds to encourage the implementation of sustainable aviation fuels as well. So it's really trying to do what we can through market-based measures, through standardizations, and through targeting, and then making sure the aircraft are ready to go the whole way.
Okay. Laura, I'm going to come to you. So you've recently joined Imperial, but you've had a long history working in the aerospace industry before kind of pitching back in. We were just talking earlier about the challenge of that cross-hopping. It shouldn't be so challenging, but it seems to be. So I guess from your perspective, what is the secret, if you like, or what is necessary to have really good industry academia collaboration? And in this space in particular, do you think there are key areas and key challenges where we should be collaborating?
So I think that the collaboration between industry and academia, there's so many different frameworks. It happily seems to work very, very well. But there are some challenges that are particularly related when it comes to aviation and to aircraft and the aviation environment, the scale, that are associated to the great complexity. So when we introduce a new technology or new change, it has a huge impact on that scale. So traditional collaboration between the industry and academia used to come at a very, we'll not say individual level, but for that specific technology. So industry goes to academia because there is that specific bucket of expertise that is not internal, needs to be complemented. While when it comes to really trying to understand which is the impact of that technology at scale, that is necessary to reduce the uncertainty about that technologies and the decision makers to make the decision where to go first or where to invest, then there is the need to look at a cluster of expertise that works synergistically together, and so probably change a little bit the model of the investment that industry have with respect to collaboration with academia. So rather than a one-one, more probably larger synergistic programs that bring together different expertise in a more synergistic way. So less siloed and more synergistic.
Okay. Ralph, let me come to you with a slight pivot. So we've been talking a lot about the technology and the technology requirements. So you're an expert in behavior. How do we think about behavior change feeding into this broader question? I mean, generally in mobility, but specifically in aviation.
Yeah, the technological advancement has been impressive, but it's not enough, right? So you talked about all the improvements in aviation, and same in car travel. We went from much less fuel-efficient cars to more fuel-efficient cars, not electric cars, fuel cell cars. But nevertheless, we have not accomplished to reduce the emissions. So if you look at the emissions in the last 30 years, like energy has reduced emissions tremendously. Also industry has reduced emissions. But for transport, it has been flat over the last 30 years, almost flat. And we simply cannot afford this anymore. So what happened is all the efficiency gains that we got were compensated by increases in demand. So we have higher auto ownership, we drive longer distances, we moved further away from our job, we fly longer on vacation, and all these things add up that the emissions remained very high in total. And so in order to make a real dent and move towards zero emissions, we need to change behavior. It cannot be just a technical solution, but we need both.
Okay. And where are the levers to drive that change?
Of course, there are a whole bunch of things that needs to be done, but it starts with promoting the most common mode of transport, which is walking. It's like 1/3 of all our trips is walking, so we need to provide safe and comfortable walk environments, but also biking. We need to promote transit. We need to introduce new modes of transport, such as ride pooling is a way to replace some of the car travel. And we also need to seriously think about restrictions. We will not achieve zero emissions if we simply think about, oh, we provide something more. We let the bus run more frequently, or we provide another somewhat more sustainable mode of transport. We need to think seriously about restrictions, how we can implement restrictions such as limiting car ownership or limiting trips for which aviation is allowed. Yeah? And that would make a true dent.
Okay, I did see a slight response from your response.
It's clear. I think it's absolutely clear. That's what we're trying to maintain people's ability and freedom to travel. It's going to take some time to get there. But yes, I fully understand. I think nobody is blind to that. The point is that with we can bring the technologies in and to try and say, well, okay, at some point you won't have to do any restrictions, but that's where we've got to get to. So and to go to sustainable fuels or to hydrogen, I mean, to change the energy, fundamentally change the energy source is where you have to go to in order to do that, and that's really what the industry is trying to do. We need to go to a different energy source.
Okay. And can I just respond to this really
quick? You can, and then I'm going to ask you to go on. I'm going to ask you to follow up. Go on.
Okay.
Yeah.
Just very quickly. So I totally agree with you. You need to work on making the aviation industry more efficient, and I appreciate the work you're doing, particularly because we don't have the political system in place right now with which we could implement the restrictions that I'm talking about. But at the same time, are we really going to achieve a system at which we are really at zero emissions? So where does the hydrogen come from? Where does the electricity come from to produce this energy? How do we manufacture airplanes? I mean, all that needs to be taken into account when we talk about zero emissions. Right?
Absolutely. I mean, I can only but agree
Yeah.
that has to be. And whenever we do our internal studies, we do look at the full life cycle of where's that energy coming from to produce the fuel to what's the emissions. And if you want to come on to emissions, then
I would like to go on. I mean, I guess
that's
just
a
before we
fundamental
move on to emissions, because I would like to come on to it. I think one kind of a very blunt tool to restrict access is to increase cost, right? But then you impact equity, and we know we won't get to decarbonisation if we don't have a just transition. And lots of things I've heard about basically talk about increasing the cost of the fuels. How do we transition in an equitable way? Do we have a sense of that, and how do we build that into the research questions? Can I ask you that? Should I start with that?
Yeah. I mean, I've been thinking about the Concorde a lot lately. And the story is very obvious. It's the best technology ever we did as aerospace engineers. The cost killed it. It was designed before 1973. It was flown after 1973. By the time it became operational, it was
too expensive.
Too expensive. Simple as that. And in that case, there was an action, a market that established itself in terms of the cost of oil has to be paid for, and the oil producers basically raised the bar. Now we are fighting a new kind of corner, which is climate change. It's the new oil producers. In a way, we have an externality on the process, which is we are affecting the environment. And then the question becomes, are we waiting for that to come and bite us, or this needs to be done through policy? So there's the policy level in which we need to basically put a cost to this in some way, either by producing the fuel, which then will come with a very high cost. All these alternative fuels are much expensive right now. It's about 3.5 times more expensive than regular fuel. And long-term scenario still goes into numbers which are multiples of the current fuel. And I don't think there will be ever a solution which is cheaper than just making a hole in the ground and getting fuel out. I think it's just obvious from the point of view of what it is. So cost will be there, and hasn't been mentioned, and it's something I've been thinking a lot about. What is the implication of this? Who is going to pay for this, and who will be able to fly in the future? I don't think any of those solutions really works out. At least we really get into these efficiency levels in which we make up for the difference by really going not 20% increase in performance, but at the level of 50%, a level in which we are making that dent on the usage of oil. And whether we have the technology is precisely the key question these days.
Okay. Rolf, can I just follow up? You said we don't have a political framework that would allow us to change in that specific way. But more broadly, everybody, I think, has mentioned policy and the importance of kind of technology engaging in the policy space. What are the policies that you think, or the policy frameworks at least, we need to move towards?
Yeah, I mean, you just mentioned equity. So I used to believe pricing is the best tool to shape transportation. And then I moved to Munich and realized that there are just people, so many affluent people, who would just buy out of any pricing scheme that you would implement, and then you have a huge equity problem. So just pricing is not the solution but it needs to be part of the solution. But it also needs things where we think about like removing parking spaces, which is then provides an equal restriction for everyone and turning these parking spaces into other uses in our cities. Or talk about restrictions like, do we need to fly from Munich to Frankfurt where we have a good high-speed rail connection, right? So these are things we need to think about. Are there some limitations where we say we simply cannot afford doing this anymore, and there we need to change? So it's a whole bundle of different policies, including new modes, but also promoting the more sustainable modes that we already have in place, and making sure that we get everybody along, right? Because otherwise we have the single parent who cannot drive the kid to soccer practice anymore because can simply not afford the toll that is raised.
Okay. So in your talk, you talked a lot about optimization and data and how that's utilized. And nobody's mentioned AI yet, which is like the first in a few weeks on a panel. But Laura, I don't mean AI, but kind of data modeling, optimization, computational design. How much is that space going to impact, do you think, the future?
Short answer, a lot.
Okay, slightly longer answer, but not
slightly
long.
Longer answer. So we have a tremendous opportunity introduced by the availability of data, and that is a fact. At the same time, there is a cost also of data, and there is an energy cost associated with data as well. So there is a huge interest in developing computational methodologies, computational approach to work in a world of data efficiency and not with the huge amount of data that we have so far, because those are associated with large energy demand to store them, to process them. But there is a huge question mark that if we wish to learn everything from data, and we get to the AI problem, then the data, the observation that we have in the aerospace world, which is the world of engineering, of scientific problems that are costly to get observation about, then we don't have all those data to build up reliable decision. And that's why we need to invest, in my opinion, a lot on the development of advanced computational method in order to leverage the great opportunity that comes from data, from sensors in the world of engineering, the world of aircraft design, and in the world of aviation at large. And in order to be able to use those data effectively, efficiently to guide the decision process. So that's a huge opportunity. It's the world of digital twin, in the sense that we can go in the world of learning from data, assimilating those with a rationale, so not randomly. And that's the big challenge. And this can really be a huge opportunity. Also, with a big impact on the acceleration of adoption of new technologies. One of the challenges that we have in aviation, when we adopt a new technology on board, is to trust the behavior that's new technology. It needs to be observed in the very different behaviors many times, statistically characterized in terms of reliability. And this requires times, investment in terms of energy to get experiments done. The development of advanced computational technologies that learn from data, but mostly from physics, and combine those two together, can accelerate the adoption because can develop strategies to understand in a faster way and characterize in a faster way the reliability of that new technology, and therefore be adopted on board earlier. This is, for instance, one of the areas where this can be helpful.
Okay. And I'm glad you brought up the energy usage, because I think I read that the global energy consumption now around data and AI is the same as the aerospace industry, right? And so you always have to question how you're using it. I was happy that you talked about alternate pollution, right? Because we framed our discussion around zero pollution and that need to think beyond carbon, and in particular, when you are thinking about decarbonisation, that you're cognizant of all the adjacent pollutants. So you hinted that there was work ongoing, but there were key questions. Could you maybe just articulate a little bit what those specific questions are around NOx and
Yeah,
contrails and
so
aerosols.
traditionally, so I, in my mind, I rate them. So CO2 is pretty simple because you produce it as the greenhouse gas, and it stays around for a long time. Then you've got contrails, which are, I can't remember how they word it in the IPCC, but it's I don't know, short-term influencing factors or something.
Sure, yeah, it's short-lived influencing factors.
Yeah, something like that, yeah. So, but they can have a cooling effect or a warming effect, and it's dependent on time of day. The general consensus is it's not good, but it's not clear exactly where, when, how they are produced, or you know, and so that's complicated. And then you've got NOx, which is even more complicated. We normally used to do NOx because it was around airports and pollution for people around airports, but then there's a whole chemistry in the atmosphere which is complicated enough depending on the water, depending on the temperature and everything. And it can even react with itself and remove itself. And I'm not a chemist, but it's complicated. And those models are not mature today. So it's very difficult. And I've had some academics in, and I say, look, I look at your model, and honestly, if I took that black and white, I'd say we should not burn hydrogen. And he says, no, that's not what we're saying.
Yeah.
We're saying, well, the model kind of suggests that.
Yeah, you have to burn it in a specific way, I think, is the
Yeah,
is the
but
answer,
then
right?
no. We think you can avoid it all by operational means. Okay, that's very nice. So then,
Yeah.
you know, then how do we prove that? How do we know what those operating conditions are? So that's really where we are. So there is now a research program in the UK on non-CO2 effects through part on the academic side to improve the models and part on the industrial side to look at the technologies. Sensors. I've said many times, I swear a future aircraft is going to have a little chemistry set at the front, figuring out what the chemistry of the atmosphere is right now to try and then say, do this, go up, go down, or inject something into the engine. I don't know what. So there's that whole problem needs to be addressed. So, and that's why I'm really pleased with the Seconia program, because, I mean, Airbus was asked to lead it because there's so many stakeholders, bringing them together. From NATS are involved, the academics, the airlines, to say what are the operational ways to get around this problem.
Okay.
So yeah, there's a lot going on in that area, but
Yeah, there's a lot.
the error bars are huge.
Okay, I'm going to open up for the audience for questions. Could you wait for the microphone to get to you there? Because we are streaming, and so we might hear you at the front, but nobody will hear you online. I think this lady here at the front, just behind Thomas.
Thank you very much. Can I just shout? Oh, there we go. Perfect. Thank you very much. Great presentation. I'm Sarah Mukherjee. I'm Chief Executive of the Global Sustainability Professionals Institute called IEMA. Now, in a few days' time, we'll be at COP talking a lot about the just transition. I wanted to pick up on this point. Surely the investment you require for these new technologies will mean the global elite will be travelling around carbon-free. The global majority will be taxed off carbon-polluting flight. I mean, should scientists be involved in being advocates for equity as well as for new science? Thank you.
I don't know if that's a question for me or a question.
I think it's, I mean, maybe Rolf, you want to say that first? I'm going to say yes is the, I think yes is the default position. Of course, scientists in the sustainability space should be advocates for an equitable transition. I don't think any of them are disagreeing with us.
We can't possibly disagree with
But
that.
how do scientists, I guess, one, consider equity in research when you start and advocate for equity? Can you talk a little?
Well, we certainly look at the different parts of segments of the population and see how they are affected differently by different policies that we implement or different improvements that we put to the transport system. And we talked about pricing. One thing that tends to be more equitable is, if I not make it more expensive, the unsustainable solution, but slower. So if I make car travel slower, that is more equitable because it affects everybody the same way. But yes, we look clearly in our transport model, we look clearly at different social demographics to understand what is the impact on different parts of the population, because I agree, we are here to provide mobility for the population and the entire population and not certain segments that should benefit more than others.
Yeah. And I think, well, and then at least at Imperial in our framework, one of the things we've built in is this kind of consideration of the impacts on equity and a just transition as technology is developed. And Bob is at the back. You should talk to Bob afterwards, I think, because he's been leading that.
Sorry to so I was interested, you talk about the elite. There are almost the same number of business jets in service that there are commercial aircraft, but they fly 10 times less. So, and we're not in that segment. We're not trying to do that part. We are trying to do the high volume people transport sector through all of this. So.
Yeah. Okay. I think one behind. And then we'll go this, and then you.
Thanks. There's one elephant that hasn't been talked about so far, which is cumulative emissions, which goes to the equity point. Nowhere on you've produced that graph, Mark.
I did, but someone did.
It's an Airbus graph going to net zero
an industry
at 2050.
Graph.
It's an industry graph.
Yes.
But you haven't talked about the cumulative emissions which drive temperature increase. And we're heading towards 3 centigrade by the end of this century. So the industry has to commit to remove all those cumulative emissions under that curve if we're going to get anywhere. Not only that, we've got 30 gigatons of historic cumulative emissions from the aircraft industry, which we've got to do something about. Otherwise, there's no question about equity.
It's an interesting point you raise. What surprised me is that when you look at the non-CO2 effects, some of the models that I've seen that show it diverging even more than the cumulative, which I find a little bit strange personally, and we're trying to get to the bottom of that. So there is a belief in the academic world that actually by just reducing the contrast, we're just talking contrast, let alone NOx, the way they express it is it could take aviation back by about 2 or 3 years in effective radiative forcing. So there's a lot of science out there still to be done. I don't know, it doesn't answer your specific point on cumulative effects of CO2, but there are other things as well that can impact, and that's where we need to get better science as well.
Okay, I'm going to reframe your question and ask the rest of the panel, and I don't know who might want to answer this, about whether there ought to be kind of policy or pricing requirements for CO2 removal on historically polluting industries. Or should I just leave it out there as a question?
I don't think I'm qualified to answer this. It's as simple as that.
Too hard? Okay, I'm going to leave it out there as a lingering question. Maybe we can all talk about it over drinks afterwards. Julia.
Yeah, so I have a question to Professor Möckel. Changing our behavior is obviously a powerful measure we all have to think about, but generally changing human behavior is such a challenge. You know, don't smoke anymore, less sugar. Just as an example, it's just almost not possible, I would say. It's very hard. So what is the most powerful measure you have in mind that we change our travel behavior?
Yeah, it's not just one solution and that will fix everything, right? But it's a combination of providing more sustainable mode infrastructure like walking, biking, transit. It's also a matter of making less sustainable modes less attractive, like making car travel slower. And I like your reference to smoking. One reason why smoking has become much less popular is because people realize there's a tremendous health impact. And it's similar for transportation. So the World Health Organization recommends that we walk, that we are active for 150 minutes per week, which is not a whole lot. But 1/3 of the population in Germany does not achieve this level. And so there's an estimation that if these people were to achieve this level that's recommended by the World Health Organization, that would reduce the number of premature deaths of those people by 30%. So it has a tremendous health impact by being active and being less bound to the car and sitting. So by telling the story and making clear it's not just about the environment, but it's also about our own health to have a better transport system, maybe that helps. Yeah? But it needs to be a combination of explaining, but also policies that restrict less sustainable modes and promote more sustainable modes. But I don't have the one policy. There's not just one lever, oh, you turn this around and then the world will be beautiful. It is complex.
I think if there was one lever, we would have found it, right? I think Aldo, and then here.
Hi, thank you for this great panel. This goes to Airbus, I think. So one thing that struck me is when we're talking about equivalences of travel time and having knobs to turn, is that in the discussions, airships as a model for inner city to inner city, national and maybe European travel would be slower in the travel speed, but equivalent if you can reach central locations. And I know that Airbus has them. I've seen the models flying in your hangars, but they don't feature anywhere in your larger promotions. And I wonder why.
So you're right, there is no airship. We have done research programs on kite assistance for ships. In fact, we deploy because we have our own ships to ship parts around. So we deploy kites for ships. We have worked with airship manufacturers, but really for communication relay nodes and not for transportation. We have seen airships more coming from the military side, not from us, for transportation around a battlefield and stuff like that. So it's not in the research portfolio, not that I'm aware of, unless I've missed something, that we have today. We are not. I've not seen any study from the company. I will certainly take it away as a question you raise, and we'll see internally if we have done anything. Because yes, you're right. There will be a travel time versus range payload infrastructure question around that, which I've not looked at.
So now we want to know where you've seen the airships. But you raised a question for me. When we first started talking about hydrogen-powered planes, there was a lot of analogies to airships and concern about public acceptance.
Yeah.
That conversation has gone quiet. Is it because
it didn't really happen? That was, I think, the thing. We were very fearful as well that this would be an instant. It's an airship. And I must admit, I think we were waiting for it, but it didn't really happen.
There is
I mean, at the end of the day, there is no way we could ever release a product which wasn't at least as safe as the current. It just would never. We would never get it certified. We would never want to do it. It's just never going to happen. So, and a lot of the challenges are achieving the level of safety.
But I think there is quite often, and this probably speaks to behavioural things. We anticipate a certain response, and it's not the actual response of the population.
Exactly. Yeah, it was very interesting.
You had a question.
That.
Thank you. We're focusing this evening on zero carbon, which is quite right and quite appropriate in my view. But when we pick up the news and read, we still see stories about hypersonic or supersonic travel, people developing these sort of really high energy, what I assume are high energy uses. And at the other end of the scale, people telling us that we'll be going around in Uber flight taxis around the city and things like that. Now, how does that fit in? Is that really going to happen, given the challenge that we've got, as we've sort of talked about?
Okay, Rafa's going to take that first, I think.
I can. I mean, I'm an aerospace engineer. I love hypersonic flight. That's the sort of thing I would love doing when I was in school. I will never fly a hypersonic flight or a supersonic flight, I think, in my life. And simply because it's not going to be a mass transportation.
You won't, or you wouldn't?
I will not.
You won't have the opportunity.
As much as I would love to.
Okay, all right. You won't have the opportunity.
Since I don't think that will happen. Now, that doesn't mean there may be a market for it, and they will need to be on the queue of the use of SAF. That's the way I will present this. They shouldn't be the first on the queue. Because typically people who fly supersonic will be the richest ones. Now we're back to your question before. I personally will be very much against it if research money goes on the direction of supporting this, and then all the actual mass transportation which we need. Is not that we can really negotiate aviation. I think all of us agree that we will be flying for the foreseeable future. We need to figure out how to solve it. Then the second is air taxis. This becomes, again, it's another niche market, but all the solutions right now are electric. So it's not that carbon becomes an issue on those designs, but by definition, those are proposed with an E in front of them. So it's an E solution. They will need to get electricity from somewhere, and again, they're competing with other sources for electricity, where the question becomes to take a car and go between airports as opposed to take an eVTOL. I would argue that the cost of the eVTOL will be much higher in terms of electricity, so most likely it will take a long time before we can get there. As technologies, I'm very much for them as we develop the technology. And then when they become practical from an economic point of view and a equitable point of view, then they will be a scale up. And that's what I would foresee to see.
Okay. Any more questions in the room? I'm very surprised Peter's being quiet. Nothing? Wait for the microphone.
Thank you. In relation to the last question, hypersonics is a defense issue predominantly, and there are different criteria for that. Looking at sustainable aviation fuels is something I've been interested in for quite some time. And in fact, one of my former students led that program worldwide, Dr. Lourdes Maurice. And that was part of the US effort in regard to that. The real challenge I see in that context is the amount of money that is required to make that an industry. And how to raise that money is really challenging. And there are cost competitive issues too. Would you certify an engine for a SAF fuel? You probably would if you were Rolls-Royce, for sure. Would you apply it if you were Airbus? Yes. But would you fill up your aircraft with that if it was more expensive? Probably not. So that becomes real issues. I'm very interested in hearing the panel's view on that.
Okay. Just
so that's where I said we're monitoring. So again, reducing fuel burn when you're flying, it's one of the questions is why bother reducing fuel burn if you're going to be running SAF anyway? Because it's going to be more expensive. So therefore, you've got to get the cost down. You don't want to be putting the CO2 into the atmosphere anyway. So you've got to get you've got to get your fuel burn down anyway. And we are seeing airlines taking up the SAF challenge. Now, the tracking of that is where it starts to get difficult because a lot of the airports, they just have one fuel system. They don't have a SAF fuel system and a kerosene fuel system. They just have one, and therefore it goes in. So you could, because SAF actually has a different burn characteristic, it does actually make sense to put it in different flights. So therefore, how does the airport know which flight to put it on so that it gets maximum benefit? So it's better to put it on a long-range flight maybe than a short-range flight. Or if you're going, we have done flights where you do get a reduction in contrails. So it's not a deal breaker, but you do get a reduction. So you want to put it where you're probably going to be verging on producing contrails, so you don't. So not all flights are equal. And therefore, managing the SAF as well between it adds another complexity as well to your question, which still also needs to be addressed.
And the other issue is so-called not all SAFs are born equal,
yes.
Which is another unfortunate set of circumstances.
Exactly, but this is where the standardization has to come in. But yes, we do speak to the scientists regularly, and they say, if you're going to fly over this part of the world, use cooking fat-based SAFs. And if you're going to fly over this part of the world, don't.
I now have a very loaded question to which I don't necessarily expect an answer. Once you make hydrogen, you can make pretty much everything.
Yes.
So why bother with hydrogen in an aircraft when you can make a sustainable, if you have enough energy, a sustainable liquid fuel with optimal properties?
Yes.
Why?
Just to say, there's lots of shaking heads in the room when you said that. When you said once you've got hydrogen, you can make anything, loads of chemists, electrochemists started shaking their head at you. So let's just leave that. I think we can leave that. You might use hydrogen to translate into other fuels. I wanted to talk just the very last question, because we are close to wrapping up. You did mention investment, and I think there are kind of lots of new technologies, emerging technologies that require a lot of investment. And that's a key to unlocking, accelerating the transition. But what else do we need to accelerate this? So from your perspective, what's needed to accelerate it? And then I'm going to ask each of the panel the same question. But maybe Mark go first.
So skills, competencies are fundamental because we are talking about technologies. But I like to say we're not trying to break the laws of physics with any of the technologies, but it is a really hard job of engineering. And it's not just with the aircraft OEM, it's throughout the entire supply chain. There's new suppliers in there that they might make scientific equipment and we say, I want an aviation grade hydrogen connector. Could I have one, please? And they go, I don't know what that means. So, and we maybe even put them off because they don't want the, so there's the whole skills, competencies, supply chain, and then the regulatory environment. The regulators are also on this journey with us because they are also trying to learn and understand how they're even going to certify a lot of this, which is why we do a lot of demonstrators. Because when we do a demonstrator, we can get the regulator in and we actually say, we're really going to fly this. It's not the final thing. Please learn with us. And that's why you see things like 0E, a lot of the test flights. It's really, if you don't fly it, you don't fix some of those key problems. You know, with tanks, you know, what happens when you're at different elevations, angles, you know, you suddenly got to think, oh, that's a problem.
Okay. Alex, we didn't speak too much about the link between that kind of sensible regulatory policy framework enabling investment, right? And I think that those two are inherently coupled. Yeah. Rolf, what's needed to accelerate?
Well, skills, right? You mentioned skill sets, and you mentioned data science earlier. We need to become better at data science to understand how to work with data, to understand what we see in the patterns, to advise policymakers. And at the same time, I would also argue engineers need to understand as well social sciences. Yeah? You mentioned if you build a hydrogen plane, but nobody wants to enter a hydrogen plane, well, that's a lost opportunity. Or I don't want to hear a transport engineer who tells me, oh, we just need to introduce, I don't know, a new train and then we will fix the world. Because I don't understand about induced demand. So we need this skill as well to understand how does society react?
Okay. Lara, any?
So yeah, a big point relates to reducing the uncertainties about that piece of technologies, but even more reducing the uncertainty that means learning more about how that piece of new technology gets integrated on board. Because there are coupling of different systems and implication of that. So adoptions of hydrogen-based means tanks, means redesigning those tanks, thinking which will be the different impact and redesign a thermal management system, reconfiguring entirely, rethinking about the configuration of an aircraft and its handling on airport. So this integration piece is what determines the impact and the worth of investment on that technology at large. And reducing this uncertainty is what will really accelerate.
Okay, thanks. I realize they've said a lot of things already. Anything left that you can add?
There's maybe one thing left, which is the dreaded valley of death between core technology, fundamental technologies and these applications. And this is one of those examples in which the urgency is so so urgent that they've really putting effort at the translation, what we were discussing at the beginning of the TUM Imperial connection, the ability for us as researchers to bring those technologies and be able to be agile on what is that we can put into the equation that can have an effect on the next 10 years. Not on the next 20 years, that's too late. It's to be early, because that's when we did those plans. To me, that's a key element of it.
Okay, that I think is a suitable end point. So thank you to our panel. I think we've heard, really, I think embedded in all of this is the importance of many voices, many stakeholders being brought together to address these really fundamental challenges and some critical areas where we need to work together along with governments and regulators and investors, but this core kind of industry-academic partnership being a critical lever, I think, in the transition. There is now going to be a showcase outside. There are some posters, some demos that come from our TUM Imperial partnership, our Zero Pollution partnership. So please stay around, have a drink, talk to some people, make new friends, catch up with old friends, and we will see you again shortly, I hope, for the next TUM Imperial extravaganza. Thank you.
This was
Thank you.
Thank you for being frank and open.